We talked about the digestive system and how you break down food as it progresses through your GI tract. Now let's talk about what happens to the substances you absorb into your bloodstream. You've seen the definition of metabolism before, back in 141, and metabolism is simply the sum of all the chemistry that's occurring in your body at one time. Pretty much everything that you eat and breathing oxygen is going to go toward the production of a molecule referred to as ATP, or adenosine triphosphate. This, to put it simplistically, is how you're going to be able to store energy in your body. And ATP is mostly produced in the mitochondria. Some is produced in the cytoplasm. And that topic is going to be a lot of the focus of our discussion in this chapter. All the variety of cells in your body have some sort of energy requirement because they have some function. Whether they're simply dividing, whether they're producing immunoglobulins, whether they're producing hormones, whether they're doing things such as conducting electric impulses for nerve transmission, whether they're causing contraction of a muscle. So all of this is going to require energy. So this particular equation is pretty much a secret of life. I didn't really type it the best way here. But if you were to look at it, C6H12O6 is glucose, which is simple sugar. So you're going to be eating food to obtain that molecule. You're breathing in to get oxygen, and it's going to result in the production of energy, which is going to be stored in the ATP molecule. And then you've got two byproducts. You've got carbon dioxide, which you'll breathe out, and then you've got water that's going to be produced as a byproduct. You'll see this referred to as metabolic water, and you'll lose that via your kidneys or through respiration, etc. So you're eating food, you're breaking it down, and you're absorbing the molecules, you're metabolizing those molecules, and you're going to be generating energy, and that energy is going to be stored in ATP, and that energy is going to be able to be retrieved for future use of energy. So you've got immediate use of ATP for cell function, and then you've got the ability to store the ATP to provide energy down the road. So if you look at this molecule of ATP right here, here's your sugar, and then these are the three inorganic phosphates. Most of the energy is stored in this last bond. So to release this energy, what you would actually do is simply break this bond, and now you've created inorganic phosphate plus ADP, adenosine diphosphate, plus you've released energy. There are two phases of metabolism. Catabolism is the breaking down of the food you ingest. Anabolism is putting it back together, whether it be used to make a pancreatic acinous cell, or a hepatocyte, or a muscle cell. So catabolism is breaking down, anabolism is building up. You've probably heard the term anabolic steroid, which people will use to help build up musculoskeletal tissue. Catabolic reactions basically are breaking down large organic molecules into smaller bits and pieces. And when they break down these molecules, they're releasing the energy that's in those chemical bonds. So this is not a terribly efficient method, and you're only going to have about 40% of the energy release that's going to be able to be used by the cells. Approximately 60% of the energy that's released when these molecules are broken down will be lost, and it's lost in the form of heat. So it's this heat that's going to give you your body temperature, your 98.6 or whatever you run. This is very much similar to the old-fashioned incandescent light bulbs. So we've moved away from using these when we can because they are very energy inefficient. They waste quite a bit of the energy in the form of heat instead of generating light. So if you've ever tried to unscrew a incandescent light bulb after it's been on for a while, you know that you really can't do it with your bare fingers because it's so hot if it's been on. However, CFU, a compact fluorescent light bulb, or even more so, a halogen light bulb, they lose so little energy that they're really not that hot, even after being on for a while, so they're much more efficient. So exactly what are the large organic molecules that we're talking about breaking down? The most common source, most common type is going to be carbohydrates. So you're typically going to be taking these things in large complex structures known as complex carbohydrates or polysaccharides. So two examples here, we'll talk about these on the next slide also, starch and glycogen. And they're called polysaccharides, saccharide meaning sugar, because they're basically big long chains that are hooked together. So a simple sugar, such as glucose, is just one unit. So that is a monomer, and this is a polymer. So what can happen here, when you release this simple sugar, it can be either used immediately or it can be stored as glycogen in skeletal muscle or as fat. There are three types of carbohydrates you should know about. The only one that is animal-based is glycogen. So this is something that your body can break down, and you'll see this in all types of meats. We do store energy in our muscles as glycogen. The two types of plant-based carbs are cellulose and starch. And cellulose is the long stem fiber that we can't break down. The bacteria in our gut can break them down, which is what produces flatulence. But things like broccoli and cauliflower, those are very high fiber plants, and they're healthier because they actually slow down our absorption of the other sugars in our gut. And it also helps sort of keep our colon cleaned out because they simply will pass on through, and most of that, again, you cannot break down cellulose in your gut. Starch is also plant-based, but your body can break it down, and your two most common food types that have starch will be corn and Irish potatoes. The second of the four types of organic molecules which you'll be digesting and absorbing will be fats, also referred to as lipids. What you should know is that the building block of these is a fatty acid, and the most abundant form that you'll have in your body is a triglyceride. So if you've ever overindulged on McDonald's French fries too often, your doctor will be able to actually see that reflected in an elevated triglyceride level in your bloodstream. So lipids and fats are a really rich source of energy storage, but it's harder for the body to break those down than it is carbohydrates, because as you'll see soon, this is going to require a higher level of oxygen, which is not always available. So saturated fats have been associated with atherosclerosis or arteriosclerosis, same thing. This is associated with animal-sourced fats, and what we're realizing now is that perhaps saturated fats were getting blamed for things that are actually due to excessive processed sugar consumption. I'm sure you've heard of saturated versus unsaturated fats. What you need to know is that saturated fats are typically solid at room temperature. They are animal-based, things like butter, lard. These, again, the traditional association is with cardiovascular disease, but now we're finding out that that's really not the case. Unsaturated fats are plant-based, and they tend to be liquid. Think of things like canola oil, corn oil. The one that is not liquid at room temperature is coconut oil. What they're referring to when they talk about saturated versus unsaturated is simply are the bonds that are connecting the carbons in the carbon chain, are they covalent double bonded or are they single bonded? So if you picture a carbon chain portion, and I'm not going to draw the whole thing, but let's say this is the end and we have all these hydrogens here. There is no place that you can actually add another hydrogen atom. So this particular molecule, if the entire thing was looking like this with all these single bonds, that would be referred to as being saturated because it's full. To convert that to a non-saturated or unsaturated fat, what you'd have to do is make a covalent bond, double bond here, and then you'd have to actually get rid of a hydrogen there. So now you can see you've got your double bonds right there. So that would now be referred to as an unsaturated fat because there is a spot right there that has not been saturated with a hydrogen. The third of the four groups of organic molecules would be proteins, the building blocks for amino acids. When you look at the amine group, which is an NH2 that's been added on to a molecule that makes this recognizable as being a protein, what you'll see is that there is nitrogen involved. So proteins can be broken down in case of extreme starvation, but the body really doesn't want to do that because when the body breaks down protein, it releases nitrogen. Nitrogen at a high enough level can be toxic enough to cause coma and death. That would be ammonia toxicity. And you'll see that in cases of liver malfunction. The group that we don't talk about as much would be the organic molecule group of nucleic acids. This is your deoxyribonucleic acid and the ribonucleic acid. That's your DNA and RNA that make up your chromosomes and such molecules as your transfer and messenger RNA in your cells. These will be broken down into the nucleotides, which are the collections of three nitrogenous bases, the base pairs. If you remember, you had adenine, thymine, guanine, and cytosine, and those will couple up according to adenine will always pair with cytosine. Adenine will always pair with thymine, and cytosine will always pair with guanine. And so that would be, one of those would be a base pair. And then a group of three base pairs would be a nucleotide. There are hormones in the body that control the breakdown of these organic substances. These are referred to as catabolic hormones. So two of these, cortisol and epinephrine, are released in time of stress. And the whole purpose of this is to increase the amount of blood sugar in your bloodstream to allow you to escape some sort of impending danger, such as cats with machine guns. So both of these will stimulate something called gluconeogenesis. If you break this down, glucose, sugar, new genesis formation. So it's formation of new sugar or new glucose. So again, this is going to increase circulating blood glucose levels. The other is glucagon. This comes from the pancreas. You may think of insulin when you think of the pancreas. But if you have not eaten for a while, then the pancreas is going to release glucagon, which is going to cause glycogenolysis or breakdown of glycogen, which will then release blood glucose into the circulation. So all of these things will increase circulating blood glucose. When you think blood glucose, you can think blood sugar. The opposite of catabolic reactions would be anabolic reactions, and these were when you're putting things together. So after you've absorbed all these building blocks, such as glucose and fatty acids and amino acids, you're going to be putting these things back together to build different parts of cells and different parts of the body. And you can also form ATP, adenosine triphosphate, in order to store some of the energy that's been created through catabolism. You'll see here a list of anabolic hormones. Testosterone, as you probably know, it will stimulate increase in muscle mass and also skeletal mass. Estrogen is going to increase fat deposition. And then coming up here, the one you may be most familiar with would be insulin produced by the pancreas. Your body's going to release, your pancreas is going to release insulin after you've had a meal. You've eaten a meal, you've digested the parts, you've absorbed the nutrients, and now the nutrients are in your bloodstream, and it's not going to do you any good until those nutrients are driven into the cells, and that's the job of insulin. The insulin is going to push the glucose into the cells. Then you also, from the liver, you've got insulin-like growth factors, the IGFs. There's multiple different varieties of those. And then growth hormone, just as it sounds, is going to be a pituitary hormone that's going to stimulate growth of the musculoskeletal system. So these are the anabolic hormones. If you've had chemistry before, you will have undoubtedly talked about oxidation reduction reactions. And to try to simplify this, all we're talking about is a transfer of electrons from one molecule or compound to another. And this occurs by the catalyst known as enzymes. Most enzymes, the vast majority of them are proteins, and they make this happen with a much lower activation energy. So what happens here, you're going to be transferring an electron from an electron donor to an electron acceptor. And the terminology you need to know is that when you give up an electron, you have been oxidized. You're going to become more positive. When you've gained an electron, you have been reduced, and you are now more negative. So some people like to use the little saying, oil rig, oxidation is losing, reduction is gaining, if that helps. And the most common compounds that we're going to be talking about in the process of metabolism, carbohydrate metabolism here, is nicotinamide adenine dinucleotide and flavin adenine dinucleotide, but you're fine to refer to them as NAD and FAD. So we're going to be swapping electrons from one form of these, from NAD to NADH, and from FAD to FADH2, and in that capacity, in that manner, we're going to be transferring energy. Because the body really prefers to utilize carbohydrates in production of ATP, that's going to be the bulk of our metabolism discussion. The equation in this slide is written a little bit differently than what was in the other slide. It depends on what reference you're using. But it's basically the same thing. So glucose, C6H12O6, plus oxygen, and they included plus water in this equation, will be transformed into wastewater, carbon dioxide, and then it's going to be releasing energy in the form of ATP. I put this slide in here so you would see the term cell respiration. This is a different term than what you see when you're talking about pulmonary or external respiration. Cell respiration is what's happening at the levels of the cytoplasm and the mitochondria. And it's talking about the conversion of nutrients such as glucose into carbon dioxide, water, and energy. This frightening looking chart is simply a summary of the way the main three organic molecules will be metabolized. And what we're going to be talking about first is going to be this section right here in the center. So this is going to be talking about carbohydrate metabolism. So we'll mention at the end of that, we'll get into a little bit of beta oxidation, which is going to be talking about fat metabolism. And then we'll give a very short mention to protein metabolism. There are three different steps in carbohydrate metabolism, and the first one is glycolysis. After you've consumed food and it's been broken down in the digestive tract, the glucose is going to be transported into the circulatory system, into the bloodstream. So at that point, it's going to be going through the liver, and it's either going to be stored there in the form of glycogen. Remember the animal-based form of carbohydrate, polysaccharides, or it's going to be used by the cells as it continues through the circulation. The pancreas is going to release the hormone insulin, and that's going to drive the glucose into the cells, and then the cell is going to host a reaction known as glycolysis. So, again, if you break this word down, glyco for glucose, lysis for destruction, so glycolysis. So glycolysis, what you need to know about it is that it happens whether or not you have oxygen present. So it is anaerobic. That doesn't mean you can't have oxygen present. It just simply means that it happens whether or not you have oxygen. And you should also know that it occurs in the cytoplasm of the cell. The very last stage ends up producing a compound known as pyruvate. I don't really care that you learn the individual steps of glycolysis, but I wanted to show you what this looks like. Understand again that this is going to be anaerobic and is happening in the cytoplasm, and at each of these individual steps you have to have a unique enzyme. So if you have any sort of defect that prevents this enzyme from being produced, any sort of mutation, this is not going to be sustainable with life. And what's happening here, you're producing a small amount of ATP, but you're also consuming a small amount of ATP. One of the big important things here is the oxidation reduction reactions which are happening with the nicotinamide. So here at the end, you see production of this compound pyruvate. That compound is going to be carried farther into the next stages of carbohydrate metabolism. One of the things I wanted to add at the very beginning of the slide, you'll see them talk about the term phosphorylation. All they're talking about is when you have glucose that is taken through the cell membrane, a phosphate ion is slapped onto it. And that actually makes the molecule of glucose too large to turn around and escape back out of the cell membrane. So it simply traps it in there. So you'll see the term oxidative phosphorylation as we progress into the metabolism discussion. So glycolysis does produce ATP, or causes it to form, storing some degree of energy. But again, it uses ATP also, so you only have a net gain of 2 molecules of ATP for every molecule of glucose that's going to be broken up. So this is representing, I guess, a Hershey's Kiss, although I do agree that it looks more like the poop emoji. But the pyruvate, which is the bigger deal here, that's going to be taken into the mitochondria if you have oxygen present. So now we're getting ready to move into the second phase of carbohydrate metabolism. The second phase of carbohydrate metabolism is referred to as a Krebs cycle, or the citric acid cycle, or the tricarboxylic acid cycle. Before we move into discussing that second phase, what happens if you don't have oxygen present, or if oxygen is not present at an adequate level? That means that pyruvate cannot be taken into the mitochondria, and instead it's going to accumulate and it's going to be converted into lactic acid. So lactic acid, if you've ever done any unexpected, more strenuous exercise than you used to, and you feel the burn, especially the next day, that's what you're dealing with, is lactic acid in your muscles. Usually it's simply a nuisance. It can actually go all the way into causing a very severe form of muscle damage. We talked a little bit about delayed onset muscle damage in chapter about muscle function. I think it's chapter 10 for most textbooks. But anyway, what will happen if you produce lactic acid when you start to rest, it's going to be taken back into liver cells and be converted back into pyruvate or glucose in something known as a Cori cycle. So that happens as you're recuperating. So we're moving into the discussion about mitochondria now, and this is a cross section. You'll actually see what they refer to as a cristae, which is going to be that inner membrane, and then the matrix on the inside. It's going to be inside this mitochondria where you have the last two steps of carbohydrate metabolism. So, but again, let's go on the presumption we are going to have oxygen present, and the pyruvate is going to be taken into the membrane of the mitochondria, and it's going to enter into the Krebs cycle. And you can see from the diagram why it's referred to as a cycle, because it actually will make two revolutions of the circle. And what it's doing is, again, this series of oxidation and reduction reactions as it's bouncing electrons from one compound to another. It's generating carbon dioxide as a waste product, but the big thing is it's accumulating more and more energy into the ATP. So here is another diagram of the Krebs cycle, and two things to note here is aerobic, which means you have to have oxygen, and it's happening inside the mitochondria. If you look, you're only producing 2 molecules of ATP net, so it's not a huge yield. And as I've written it this way, 2 times 1, simply because, again, you're going to be making 2 revolutions of the cycle. And just like what you saw with glycolysis, you're going to have a unique enzyme at every step. Your ending product at the completion of 2 revolutions of the Krebs cycle is a compound known as acetyl-CoA. However, the most important product of the Krebs cycle is going to be production of the molecules NADH and FADH2. These are going to be basically the results of the oxidation and reduction reactions, and they're going to be transferring electrons into what's known as the electron transport system or electron transport chain. And this is going to be the third and final step of aerobic metabolism and carbohydrate metabolism. The inner membrane of the mitochondria is studded with enzyme complexes and what's known as coenzymes. And these are going to be proton pumps and electron carriers that are going to be bouncing hydrogen ions. Remember, these are simply hydrogen atoms that have had the electrons stripped down. And these are going to be pumped into the spaces between the 2 mitochondrial membranes. And so as it's bouncing along these hydrogen ions, you're bouncing along electrons. And at the very end, you're going to have an electron acceptor, which is oxygen, which is why you have to have oxygen, which is why this is called aerobic metabolism. And you're going to end up forming water as a waste product, but you're going to be producing the highest yield of ATP of the entire carbohydrate metabolism process. You'll see this referred to quite often as oxidative phosphorylation. So we've talked about how you eat to obtain glucose, and I mentioned when you looked at the equation where energy is being produced, there is an oxygen input that's required, and this again is why. This is why you have to breathe. Oxygen is going to be the very final electron acceptor for the electron transport chain. Otherwise, the free radicals that are produced through this process will be very damaging to cells and tissues. This way, it simply forms water and is harmless. I showed you a cross-section earlier of a mitochondria, and that's what this schematic represents. So here is an outer membrane of the mitochondria, here is the other side of it, here is the inner membrane of the mitochondria. And these are representing the cytochromes and coenzymes that are embedded into the cristae, and then you've got the matrix in the center. So what's happening here, again, here you see the citric acid cycle, the Krebs cycle, and then you see the electron transport system happening here. So the most important thing that's happening with the energy that's being contained with the NAD and the FAD is going to be that this energy is going to be used to actually pump hydrogen ions across that inner membrane. And it's going to end up with an accumulation in that space where you've got a gradient of protons. Remember, a gradient being defined as a high concentration on one side and a low concentration on the other, and setting up this concentration gradient that's going to result in something known as chemiosmosis, which I'll define on the next slide. So look at the term osmosis. Remember, osmosis is defined as the passive flow of water across a membrane that's going to equalize some sort of gradient. You can have gradients based on different things. You can have gradients based on voltages, charges. You can have a gradient based on particulate size. In this case, we're talking about a gradient based on hydrogen ions. Remember, a hydrogen atom simply has one proton and one little electron. And so when you lose that electron, when you strip it away, you're simply left with a proton. So what's happening here, the energy that's being carried from the Krebs cycle and the NADH and the FADH2 is going to be used to forcibly, actively pump protons through those that inner membrane of the mitochondria, and it's going to set up a gradient. And then what's going to happen is when the hydrogen ions finally hit a critical tipping point, they're going to rush through this membrane embedded protein pump that's called ATP synthase. So this is the ultimate site or ultimate definition here of oxidative phosphorylation. So the electron transport chain is where oxidative phosphorylation is happening. Here is a closer look of that little proton pump. Again, this is an enzyme, and it's in the inner membrane of the mitochondria, and it's referred to as ATP synthase simply because, remember, the ASE means it's an enzyme, but it's producing ATP from ADP. So again, here is this crystal wall. This is going to be representing the matrix. And so what's happened is you've pumped all these hydrogen ions over into this side. You've built up this big gradient, and now the hydrogen is going to go through this ATP synthase. It's going to force this little turbine-like apparatus to basically turn, and it's going to manually compress energy, adenosine diphosphate, and an inorganic phosphate into the molecule we know as ATP. So now over here we have energy storage, and that energy is going to be available to cells to perform their normal work, again, be it movement, transmission of impulses, growth, or whatever. So this is a summary of what we've talked about when we're talking about glucose metabolism and cell respiration. And I realize this program that I use to record this has cut off the last sentence, but I can tell you about it. So the big point I'm trying to make here is, again, you're only getting a couple of ATP formed during glycolysis. During the Krebs cycle, you're getting a couple more. But what the big takeaway here, what you can't see, is the entire net total of ATP per molecule of glucose is going to be 36. So you're going to end up with approximately 32 ATP molecules being produced during the very final stage in the electron transport chain and oxidative phosphorylation. So by far the most productive phase of carbohydrate metabolism is the oxidative phosphorylation that happens at the electron transport chain. So what does this mean on a practical basis? Let's say that you are walking on a treadmill and you're walking along about 2.5, 3 miles an hour, and you've got enough energy, you've got water, you're able to breathe comfortably, you can even talk to the person on the treadmill next to you, and you could walk for hours. You may die of boredom, but you could walk for hours. However, what if somebody cranks this thing up to about 5 miles an hour, and now you're having to actually jog or run? Your muscles are having to work a whole lot harder. they're going to need a whole lot more oxygen to be able to maintain the muscular contraction cycles that's happening millions of times, billions of times per minute here. And so you're going to have to breathe a whole lot faster to get this increased oxygen in. And you're requiring a whole lot more energy to maintain this muscular contraction. There's going to be a point, for me it would just be a few minutes into this. If you're really fit, it may be a little bit longer before you hit that point, that you're not able to get enough oxygen in your body to convert enough energy in the ATP. So basically you're going to run out of energy to be able to maintain this action. So at this point, you've got pyruvate that's accumulating in the cytoplasm, and you keep on going, and this is going to be converted into lactic acid. Now you're going to be sore tomorrow, and pretty soon you're going to run out of energy, and you're simply going to collapse off the treadmill onto the floor. So what's happened is you went from aerobic metabolism, where you're able to get enough oxygen to maintain your work, into anaerobic metabolism, where you weren't having enough oxygen consumed to be able to maintain that production line coming through the Krebs cycle and the electron transport system. So again, think about this in summary. Glycolysis, you don't have to have oxygen present, but it's only producing a couple of molecules of ATP per molecule of glucose. The bulk of your ATP production comes from aerobic metabolism, where you have to have oxygen. So this doesn't mean that it's totally shut down. You'll still have some energy being produced that way, but you're not having enough oxygen to be sending all of that pyruvate into the last two phases of carbohydrate metabolism, into the stages of aerobic metabolism. So that's the three phases of carbohydrate metabolism in summary: your glycolysis, your Krebs cycle, and the oxidative phosphorylation happening at the level of the electron transport system. So I want to give you some definitions now. Gluconeogenesis, again, if you break up these terms, they'll make more sense to you. You've seen this one before: gluconeogenesis, formation of new glucose. And this might be from pyruvate. It might be from lactate, like you would see in the Cori cycle. This happens primarily in the liver, and it's happening during times that you don't have enough glucose in your system because you haven't eaten for a while. So if you've been fasting, if you're in a period of starvation or a low-carb diet, one of what they can refer to as a ketogenic diets, you're going to have to rely on your body, your liver, to actually form molecules of glucose. You can simply look at this chart and you'll see glycolysis and gluconeogenesis are basically the opposite pathways from each other. Glycogenesis is the formation of glycogen, just as it would sound, and glucose molecules are simply added together to form the polymers of glycogen. And you'll also see this in the Cori cycle, and you'll also see it stimulated by insulin after you've had a large sugary meal. The opposite of glycogenesis is glycogenolysis. So again, break this term down. So you've got destruction of glycogen. And so this is going to be stimulated by things like glucagon and adrenaline. You haven't had anything to eat for a while, or your body thinks it's needing a whole lot of blood sugar to respond to stress. And so it's going to be breaking down glycogen to increase blood sugar. So make sure you understand, when you break down glycogen, you're increasing blood sugar. When you're forming glycogen, you're going to be decreasing. So this relates back to the hormones we talked about at the first of this discussion, the catabolic versus the anabolic hormones. So here is a summary of the different terms, and so please make sure you understand these. It's glycogenesis, glycolysis, gluconeogenesis, and glycogenolysis. Let's switch gears and talk about how we metabolize fats. When you've eaten something, and just about everything does, that contains fat, a hormone called CCK cholecystokinin is going to be released that's going to stimulate gallbladder contraction. It's going to stimulate pancreatic secretion. And this is going to aid in digestion of fats. Remember that digesting fats has to do with emulsification, which is not a chemical digestion, but it's a type of physical digestion or physical breaking down of the large globules of fat. So the bile salts will emulsify the large globules of fat, and that way the pancreatic lipases, or the enzymes, remember the ASE means enzyme, will go ahead and continue the breakdown of these fats, and you'll end up with the free fatty acids that are small enough for transport across the intestinal membranes. Remember from the digestive chapter that the villi and the microvilli of the small intestine have at the center a lymphatic capillary referred to as a lacteal, and it's these lacteals that will be taking in the broken down emulsified fat. The resulting chylomicrons are going to be transported from the lymphatic system into the circulatory system, and they'll go to either the liver or they'll be stored in the fat cells. This slide is just a reminder of what these villi and these lacteals look like if you don't remember from the digestive discussion. So these projections, these finger-like projections, are your villi, and then at the center of these you'll have the lacteal. So as you've just seen, carbohydrates and lipids are absorbed differently from the intestinal tract, but they're also metabolized differently after they've been absorbed. You still have the same chemical compounds. You've got carbon, hydrogen, and oxygen that comprise lipids, just like you do with carbohydrates, but the ratio is different. If you remember, with carbohydrates, you always had that carbon, hydrogen, oxygen ratio of 1 to 2 to 1. Remember, glucose was C6H12O6. Well, with lipids, you've got less oxygen. So while lipids are much more energy dense than carbohydrates, they're more difficult to break down. The big difference in fatty metabolism is going to be the initial steps, referred to as lipolysis, and this is going to be referred to as beta oxidation, and at which point the products of this, you'll end up with very similar to the products of what you ended up going into the Krebs cycle, the acetyl-CoA. So it's just the initial breakdown that has to differ before you end up moving into the same cycles, the Krebs cycle and the electron transport system that you started out with in carbohydrate metabolism. So in other words, you've got beta oxidation instead of glycolysis. If you remember that the metabolism of carbohydrates, you ended up with roughly 36 molecules of ATP for every molecule of glucose. With fat, you end up with 144 molecules of ATP for every molecule of fatty acids. So you see it's much more energy rich, but because of the increased oxygen requirement, it's much more difficult for the body to get to. That's why when you're exercising, you're going to be burning off carbs before you ever get to the anaerobic phase of exercise that's going to allow you to break down fats. So as I stated on the previous slide, you have to actually burn through your available carbohydrates before you do start burning these fats. If you do get your blood sugar low enough, then these triglycerides will go through the beta oxidation into the acetyl-CoA, and then the acetyl-CoA molecules again will go on through the Krebs cycle and through the process of ATP generation using normal aerobic respiration. The most metabolically active organ that you've got in your body is the liver. The least metabolically active organ you've got is the brain. So the brain does not have any reserve of nutrition, so it's going to have to be supplied steadily with sugar for function. So this is one of the reasons that the body has these backup systems, that if you aren't able to get enough blood glucose, then you can actually convert the fatty acids and even ketone bodies into glucose. Fat and other lipids are going to be transported through the bloodstream in the form of a lipoprotein. Lipoprotein has a core of fat and cholesterol and has a lipid membrane that contains proteins referred to as apolipoproteins. There are many types of lipoproteins, but the ones that we discussed most are the LDL and the HDL. These lipoproteins get their name based on how they interact with a centrifuge, and so the low density and the ultra low density lipoproteins will actually basically be higher in the spun out sample because they are much less dense. So if you look at the bottom here, if you've got more protein and less fat, then it's going to be a heavier or HDL or high density level lipoprotein. If you have your cholesterol checked on a blood workup, they'll give you several numbers. They're going to give you a total cholesterol level, then they'll give you an LDL and an HDL. The LDL is a low-density lipoprotein, and you like to see that number as low as possible because that's the one that has been traditionally associated with arterial plaques and atherosclerosis, more commonly known as hardening of the arteries. The HDL, high density, tends to be your good cholesterol, and they will like that to be much higher than your LDL. So the most meaningful thing that they'll actually give you is a ratio between the LDL and the HDL. So then the other two I have listed here, these really aren't looked at too much, the intermediate density and the very low density lipoproteins. If you've gone for a long period of time without eating, your body will have expended its available carbohydrate reserve and will move into breaking down fats and proteins. So what can happen is the oxidation or the breakdown, the beta oxidation of too many fatty acids can actually overload the Krebs cycle, and the extra acetyl-CoA is going to be converted into something called a ketone body. Ketone bodies can, as I mentioned earlier, can serve as a function of glucose, especially for the brain, but however, it can build up to unhealthy levels. You'll see this in somebody that's got a case of non-regulated diabetes mellitus, or if they've been through a prolonged period of starvation. Excess ketone bodies can be converted into ketoacids and can result in an overwhelming case of ketoacidosis, which can be fatal if not corrected. So one of the things that's characteristic about this is that person's breath will have a very sweet, rotten meat type smell. It's very recognizable once you've smelled it. Although there is a popular diet plan going around now called the ketosis diet. Most of the time when we talk about ketosis, we're talking about ketoacidosis that you'll see again in unregulated diabetes mellitus. So finally, let's take a quick look at protein metabolism. There are so many different forms of proteins, and they're all metabolized in slightly different ways. So this number is probably pretty low. I've seen published up to 200,000 different types of proteins in the body. And remember, these are all composed of 20 different amino acids hooked together in some various form or another. Very similar to how you take 26 letters of the English alphabet and you can fill dictionaries with all the words of many different languages from those 26 letters. The body, as I mentioned earlier, does not really want to metabolize protein, and one of the reasons for that is because then it has to deal with processing out the ammonia. So proteins will be broken down only if you've run out of carbs and fats. We store excess carbs that we consume as glycogen, and we store excess lipids that we consume as fat. But protein's not going to be stored. So if you eat too much protein in your diet, it is going to end up being converted into either a carb or a fat. When you consume proteins in your diet, they're going to be digested down into amino acids, absorbed that way, and then they're going to be reassembled. Of the 20 amino acids, 10 are considered non-essential and 10 are considered to be essential. What this means is that the essential amino acids have to be included in the diet because your body cannot manufacture those. So that number is a little bit higher for children. This is for adults. As a reminder, proteins start to be digested in the stomach with the addition of pepsin and hydrochloric acid. After the initial breakdown of proteins in the stomach, they'll progress to the small intestine. The enteroendocrine cells of the duodenum are going to release secretin and cholecystokinin, which will stimulate pancreatic release of the proteases such as trypsin, chymotrypsin, and elastase. These enzymes are going to further break down the proteins into the individual amino acids for absorption. The proteolytic enzymes released by the pancreas are so effective in dissolving flesh that you would actually be autodigested if they were not released as an inactive form. So what they refer to as proenzymes are released into the small intestine, and there they're activated into the active form. And the mucus coating, that rich mucus slime lining the intestinal tract, is what prevents you from self-digesting. As I mentioned earlier, your body really does not want to process the nitrogen that's going to be released when protein is digested. So protein is your body's least favorite thing to have to metabolize. So remember the amine groups, or the NH2s that make up the amino acids. There's an event referred to as deamination, which the amine group is removed, and then the nitrogen is going to be used to create an ammonium ion. And that ammonia has to be gotten rid of safely by the liver to prevent a toxic buildup of ammonia in the bloodstream. In fact, one of the things that can happen with acute liver failure is a buildup of ammonia in the bloodstream and coma and death if that's not treated. So the ammonia is going to be combined with carbon dioxide, and it's going to form what they refer to as urea, along with some wastewater, and then the urea is going to be safely eliminated through the kidneys. So this is what it looks like. The ammonia that's been formed in the liver is going to be going through the urea cycle, and that's going to be excreted by the kidneys, and therefore one of the classic markers that you'll look at for kidney damage in blood is going to be the blood urea nitrogen, or BUN level, although it can be increased from things as simple as dehydration. When you do your reading about the processes of metabolism, you'll see them referred to a couple of different phases of the body, and I'll just mention them here to be complete, and as a reminder, talk a little bit about the hormones associated with each state. The absorptive state is the first 8 to 10 hours after you've had a meal. At this point, you've got food in your GI tract being broken down and being absorbed. Insulin is going to be released from your pancreas to drive the glucose into your cells. And so, in other words, your body is processing the glucose that you've taken in. So with a post-absorptive state, you've not eaten for a while. This might happen, for most people, it only happens overnight if you don't eat late at night. This is what they refer to as the fasting state. And the hormone associated with this is the pancreatic hormone glucagon. So let's say it's been 12 to 14 hours since you've eaten, your body's getting low on circulating glucose, and so now the glucagon is going to start breaking down glycogen to release glucose to increase your blood sugar. So insulin is going to decrease your blood sugar, and glucagon is going to increase it. Let's change direction a little bit now and start talking about energy and heat balance. We talked about the fact that through the process of metabolism and breaking down molecules, you're releasing energy, and about 40% of that energy is going to be used for actual work performed by the cells, and about 60% of that is going to be lost as heat, and that's going to give us our body temperature. You have a pretty narrow homeostatic range of temperature, and this is one of those examples of negative feedback that we talked about very early on in this course. So the thermostat for your body is actually located in the hypothalamus of the brain, and if the body temperature is getting too high, the hypothalamus is going to tell the sweat glands to start to sweat. You're going to affect vasodilation. You're going to increase the vasodilation near the skin. You're going to try to move your blood flow more toward the superficial areas, so therefore when you sweat, the evaporative cooling will dissipate the heat and lower your body temperature. On the flip side of that, if you're too cold, then you're going to vasoconstrict near the skin. And that's why if you're really, really cold, your fingertips and your lips might look a little bluish. So when you're really cold, you're going to vasoconstrict under the skin. And then if you're cold enough, you're going to actually generate your own heat. And this is referred to as thermogenesis. There are two types of thermogenesis, and after infanthood, we use shivering thermogenesis to keep us warm. This is a very effective way of generating heat. If you recall, with muscular contraction, one of the last phases is going to be the breakdown of the cross bridges between the actin and myosin myofilaments. This breakdown requires the release and kicking out of a molecule of ATP, which again, remember, energy, heat. So the more movement you produce, then the more heat you're going to produce. This is why we tend to get hot and sweaty when we exercise more. But with shivering, you've got contractions, microcontractions of opposing muscle groups. In other words, agonist muscles and antagonist muscles. So therefore, you don't get this gross overall big movement. You just basically stand there and quiver, and all these little microcontractions are able to produce a pretty good amount of heat to warm up your body when the hypothalamus has sensed that it's cold. Non-shivering thermogenesis is something that you see primarily in infants, although it would be awfully nice if we could do this as adults. Brown fat is called that because it looks sort of a reddish brown in appearance when it's exposed, because it's really rich in mitochondria. So this brown fat, you'll see the distribution pattern here on this diagram of an infant. Babies can't shiver, and so the brown fat is really the only way they can generate heat. This is why infants are so susceptible to the effects of cold. When an infant's born, they cannot thermoregulate any better than a snake. That's why you'll see people really rushing to bundle them up and put the hats and blankets on them. So the other type of thermogenesis that is non-shivering is an endocrine acclimation. This will be something that will be produced by thyroid hormone. You'll see an example of this. If somebody is hypothyroid, then they tend to be usually overweight, sluggish, and they're cold all the time. Whereas if you've got somebody that is hyperthyroid, they tend to be very fidgety, very nervous in actions. They tend to be thin, and their body temperature actually will be a little bit warmer than somebody with a normal thyroid level. So to recap, the non-shivering thermogenesis in infants is due to brown fat, and that color comes from the high concentration of the really highly metabolically active mitochondria. Unfortunately for us, after we leave infanthood, we can no longer use that non-shivering brown fat metabolism, and so we'll either be shivering, or over a long period of time we'll get a small amount of acclimatization, the non-shivering thermogenesis that's going to be stimulated by thyroid hormone. As I mentioned earlier, along with forms of trying to produce heat through thermogenesis, your body will use mechanisms such as vasoconstriction to try to control a heat loss. Sometimes your body can actually do some pretty serious damage by doing this. An example would be frostbite. So again, what's going to happen when you get really cold, you're going to vasodilate in your deep core to bring the blood to your deeper, warmer center, and it's going to vasoconstrict superficially. It can actually vasoconstrict so much that you lose circulation to your fingers and your toes. This loss of circulation can be so extreme that you end up with gangrene and you can actually lose those digits. So moving from talking about when it's too cold, when it's too hot, there are four mechanisms of heat loss that the body will use to try to maintain that homeostatic range of temperature. The methods of heat loss would be conduction, convection, radiation, and evaporation. The type of heat loss that occurs when your skin comes in contact with an object is referred to as conduction heat loss. When you get up from your seat, the chair surface will be warm, and that's because you've lost a very small amount of your body heat to that chair surface. Slightly more important would be convection heat loss, and this is when your body heat is going to be transferred to the air that surrounds you. So convection heat loss is responsible for about 15% of your body heat. Most of your body heat is actually lost through radiation. So an example, if you feel the rays of sun warming your body, that's an example of radiant heat. So if you've stood too close to someone and you feel their body heat, that's an example of radiant heat. Then finally, evaporative heat loss is when you transfer heat by the evaporation of water. This occurs if you're exercising or if you're running a fever. Your hypothalamus is going to detect a potential increase in your body temperature. It's going to detect the need to dissipate that heat. So it's going to stimulate your sweat glands to start to sweat. And as air molecules move across that sweat, it's going to be picking up heat that's being dissipated from your body. If you're in a very humid environment, then sweating and evaporative heat loss is not going to be very effective. But the reason for that is that the air, when it's very humid, already contains a great deal of moisture, and so it's not able to pick up moisture from your skin. Death from hyperthermia is a lot more likely in a really high temperature, high humidity environment. There are several things that affect thermoregulation, and one of that's going to be the surface area of the body. A skinny person is going to feel colder than a heavy person typically, and that's because their ratio of their body surface area to their body mass is going to be a much lower ratio. There are other things that affect thermogenesis and average daily temperature. Weight distribution, tissue types. If you tend to carry more weight in fat, then you're going to retain heat more than if you're a very muscular person. If you're more muscular, you're going to actually generate more heat. So also, your average temperature is going to be higher in the late in the evening. You'll tend to cool off at night. That's one of the reasons that pediatricians will tell moms to check for fever in their children in the early evening hours. The other thing is ovulatory cycles for women. That actually used to be the basis of some forms of birth control. If women were trying to get pregnant, they would actually check their daily temperature, and when it would go up a little bit, then they knew it was time to try to achieve pregnancy because it was more likely to be in tune with ovulation. Let me give you a couple of definitions here. Pyrexia simply means an elevated body temperature. Fever is defined as when your hypothalamic set point has been elevated. I'll give you an example. Cytokines are part of your immune system. They're in your bloodstream, if you recall. And the cytokine 1 will actually tell your thermostat to reset in your hypothalamus when you've been infected with something like a cold virus. So now instead of saying, okay, your body temperature should be 98.6, it might say your body temperature should be 101. So then your body will start to try to generate heat to make up that gap. That's where the chills and fever comes from. Chills and shivering comes from when you're incubating a fever, because your body's trying to increase your body temperature to match that set point. So hypothermia is when your set point is normal, it's still at 98.6, but you've done something to overheat, and your actual body temperature might be 103, 104. Things like being trapped in a locked car in a hot day, something like that would cause hypothermia. Traditionally, parents have given children medication as soon as they run a fever to reduce their temperature, but that's not always the first thing that we should do. The fever is actually a reaction of your immune system to try to fight off an infection such as a virus. And as long as it's not dangerously high, we should let it run its course. As adults, what we tend to do, if we're not feeling or we're running a fever, we'll pop some Tylenol, pop some Motrin, knock our fever down, we feel better. Then we go to work or go into social settings, and we're still shedding the virus because we're highly contagious, so all we're doing is just disseminating our viral infection through the community. So unless you're really feeling extremely badly, sometimes you should let the fever take its course. So if you do take something to lower your temperature, what you're doing is resetting the thermostat. You're readjusting your hypothalamus to go from 101 back down to 98.6, and that's why you sweat so much after you've taken an antipyretic, such as a nonsteroidal anti-inflammatory. This is what your mother would have referred to as sweating off your fever. I included this in here just as a little PSA here. The signs and symptoms of heat exhaustion, which if not relieved or treated can lead to a heat stroke. There are some conditions that can make you more prone to heat stroke. One of these is congestive heart failure. Another is the use of the antibiotic erythromycin. And then finally, the third is a term I would like you to be familiar with, anhidrosis. You may remember the term hyperhidrosis means when you have unexplained, not as a result of activity type sweating. And anhidrosis means you can't sweat. And if you can't sweat, then when you do start to overheat, you don't have any way of trying to have an evaporative cooling there. So anhidrosis can definitely make you have to move to a different environment to make you less prone to heat stroke. So let's use the last bit of this chapter to talk about nutrition. First, let's give you a definition of the metabolic rate. Your metabolic rate is how much energy that you're taking in versus how much energy you're putting out. So your BMR, your basal metabolic rate, is how much energy you're going to expend when you're doing absolutely nothing in a very neutral environment while you're in the post-absorptive state. In other words, you haven't eaten anything for at least 8 to 12 hours. This is very, very difficult to calculate. You have to have special equipment to do this, and so usually your BMR is simply calculated from a formula, which is pretty inaccurate, but gives you some idea of the difference in your BMR at different stages of your life, and as far as age, and also between the two genders. If you look at this, your metabolic rate, most of it actually comes from all of the functions of your organs during the day, and only about 20% comes from physical activity. About 10% is the amount of energy expenditure that's required to keep your body temperature in the homeostatic range. So this rate will be a little bit higher if a person is exercising, they're more active, or if they're a leaner body composition. So it's always seemed a little bit grossly unfair that if you've got a really fit person sitting in a lecture hall, they are, by definition, with your metabolic rate, burning more calories sitting still doing nothing than an unfit person doing the exact same thing. As you age, your composition of your body is going to be changing. You're going to have decreasing levels of muscle mass and increasing levels of fat. And this is one of the reasons that your BMR is going to decrease. So in other words, that's why it's harder and harder to keep weight off as you get older. You have to eat less and exercise more. When we discuss our BMR and the amount of energy we need to consume on a daily basis, we talk in the lingo of calories. The nutritional calorie, capital C calorie, is defined as the amount of heat it's going to take to raise a kilogram of water by 1 degree Celsius. So when we talk about, again, nutritional calories, we're talking capital C. On average, an individual is going to need between 1,500 to 2,000 calories per day to maintain normal, non-strenuous activities. That number is going to depend on your body mass, your age, your overall build, and your gender, as well as how much activity you're putting in on a daily basis. As I mentioned early on, your body had much rather metabolize carbohydrates than fats or proteins because it's much easier to do so. Overall, and this should be kind of common sense, how much weight you're going to gain over any stretch of time is going to depend on the amount of calories you eat versus the amount of calories that you burn. So to actually lose weight, you're going to have to burn more calories than what you ingest. Let's take a closer look at some aspects of nutrition, such as vitamins and minerals. Vitamins are defined as organic compounds inside food that you'll get from consuming fruits and vegetables. There are a few vitamins that your body can actually synthesize, and then there are some that you'll actually have to take in. Vitamins can be described as being either fat soluble or water soluble. The fat soluble vitamins you should know are A, D, E, and K, and you have to have fats in your diet to be able to absorb these particular vitamins. So, because you store these vitamins in the fat of your body, you can actually overdose on these things, and that's referred to as hypervitaminosis. Vitamin A, fat soluble. This is an important aspect of pigment found in the retina, referred to as opsin. You may remember rhodopsin. And if you have a deficiency of this, one of the first symptoms that you'll see is night blindness. If you're overdosing on vitamin A, if you have a hypervitaminosis A, in other words, acute symptoms would be things like drowsiness and abdominal pain, nausea and vomiting. You could even have increased cerebral pressure. Chronic vitamin A toxicity would include blurry vision and bone pain and bone swelling. You can also have dry, rough, itchy, peeling skin and cracked fingernails and mouth ulcers. Also, fat soluble is vitamin D, and this is going to be created in the skin secondarily to ultraviolet radiation. Typically, sun exposure is the way that we get most of this. And this is critical because of the hormone calcitriol, which is created from vitamin D in the kidney. A lot of references will actually refer to calcitriol as simply another phase of vitamin D. Without this particular hormone, you're not going to be able to absorb calcium and phosphorus from your diet through your intestinal tract, and you'll end up with severely weakened bones. Excess vitamin D can cause overcalcification of the bones, soft tissue, heart, and kidneys, and you can also acutely see dehydration and vomiting. Fat soluble vitamin E is very important for cell membrane health and healthy skin. It is linked to selenium, so if you have an overdosage of selenium, you're going to have a deficiency of vitamin E and vice versa. So the ratio between selenium and vitamin E is very important. So, like all the other fat soluble vitamins, you can definitely overdose on these because you store these in the lipids of your body. E and A are antioxidants, but they have shown, contrary to popular belief for a while, that taking high doses of A and E are not actually preventive of disease processes. It's simply important to get normal doses from your regular food sources. It's always much better to get your vitamins from fresh vegetables and fresh fruit other than in a pill, which is usually poorly absorbed. And then the last fat soluble vitamin we'll discuss, vitamin K. This is very essential for blood clotting. Without vitamin A, you're not able to form some of the clotting factors that we discussed in the hematology chapter. In fact, vitamin K is important enough that if you go to the emergency room for unexplained nosebleed or epistaxis, one of the things that they will do is give you a preventive dose of vitamin K. The water-soluble vitamins, the ones we talk about most, are the 8B vitamins and then vitamin C. Now, you can absorb these with simple water through the digestive tract, and then, of course, you lose them pretty easily through the urinary system. So, the condition associated with improper dosing of water-soluble vitamins is hypovitaminosis because you can't store these in your body. The bacteria, the normal flora that live in your large intestine, They produce vitamin K. They also produce 5 of the water-soluble B vitamins: biotin, riboflavin, thiamine, folic acid, and pantothenic acid. If you remember from the digestive tract chapter, we talked about intrinsic factor. Intrinsic factor is produced in the stomach, and it's a carrier protein that's essential to be able for vitamin B12 to be absorbed through your intestine. If you end up not being able to absorb B12 for some reason, you'll end up with an anemia due to hemoglobin deficiency, and that's referred to as a pernicious anemia. This is one of the issues you could see with someone who's had a gastric bypass or some sort of stomach surgery that required removing the part of the stomach that produced the intrinsic factor. They're not going to be able to absorb vitamin B very easily and will have to be on supplementation the rest of their life. If the vitamins are going to be the organic nutrients, then the minerals are going to be the inorganic nutrients. We cannot make these, we have to eat them, and then we store quite a bit of these in the body. So the most common ones that we'll talk about, and you should recognize the necessity of these from discussions earlier about muscles and nerves: potassium and sodium, calcium, phosphorus, magnesium, and chloride. And it should be pretty obvious to you that we store a tremendous amount of our calcium and phosphorus supplies in the skeleton. Most of the minerals that are in your body are in the form of ions, and the sodium and chloride ions are the electrolytes that we talk about along with potassium when we speak of things like muscle contraction and nerve transmission. Trace minerals are referred to as such because we only need them in very small amounts, but they are still essential for normal functions such as magnesium and zinc. Well, you survived this chapter. It's no one's favorite. I hope it wasn't too painful, and I'll see you next time.